Good day. I am Geoffrey Mendiola, and alongside with me are my groupmates Jomil Almandres and Ron Michael Nene. We will be presenting the IEEE 242-2001, Chapter 15, Overcurrent Coordination. First, we have the general discussion. The objectives of overcurrent coordination are to determine the characteristics, ratings, and settings of overcurrent protective devices that minimize equipment damage and interrupt short circuits as rapidly as possible. Protective devices are applied as primary and backup protection. The protective device settings should be determined after the design and all load and fault currents have been calculated. A preliminary coordination study should be made to verify that the protective device ratings can be selective and that the source utilities protection practices have been considered. Primary protection is the first line of defense against damage caused by a fault or other abnormal operating condition. As a precautionary measure, additional protection is generally provided and is called backup protection. A backup device should be able to withstand the fault conditions for a greater time period than the primary protective device. Methods of backup protections can be relay backup, breaker backup, remote backup, and centrally coordinated backup. For 15.2, we have the general considerations when making a coordination study. The following information on short circuit currents for each local bus may be necessary. The maximum and minimum first cycle momentary single and three-phase short circuit current, 1.5 to 8 cycle interrupting duty three-phase short circuit current, 30 cycle three-phase short circuit current, and ground fault current. The momentary currents are used to determine the maximum and minimum currents to which instantaneous and direct acting trip devices respond. The maximum interrupting current is the value at which the circuit protection device coordination time interval or CTI is most often established. The minimum interrupting current is needed to determine whether the circuit protection sensitivity is adequate. The 30-cycle fault currents with no motor contribution may be used to set the CTI for time over current protective devices in the system. When faults occur on the secondary of delta Y grounded transformers, the per unit fault current magnitude in each phase depends on the type of fault. For a phase-to-phase fault in the secondary of a delta Y transformer, the per unit primary line current in one phase is approximately 16% greater than the per unit secondary line current. Also, the primary winding current for a three-phase secondary fault is approximately 16% greater than for a phase-to-phase secondary fault. For a single phase-to-ground fault on a solidly grounded transformer secondary, the per unit currents in two phases of the primary are only 58% of the secondary fault current. For a three-phase fault on the transformer secondary, the primary winding current equals that for a single phase-to-ground fault. For this condition, the primary protective device characteristic curve should be shifted to the right or the transformer damage curve should be shifted to the left by 58%. A load flow study should be made to determine the normal and emergency load currents at each load center and through each branch circuit. The load current data are used to establish conductor, equipment, and protective device continuous current ratings. Another consideration is the pickup. Pickup is defined as the minimum current that starts an action. The pickup of an overcurrent protective relay has generally been considered the minimum value of current that causes the relay to close its contacts. We have pickup for electromechanical versus static relays, low voltage circuit breakers, MCCBs, and fuses. The pickup value for electromechanical induction disk time over current relays is the minimum current that causes the disk to start turning and ultimately close its contacts. The tap or current setting of static relays usually correspond to the pickup current. Also, the trip time is much more accurate, especially in the range of 1 to 2 times minimum pickup. MCCBs with thermal tripped elements generally carry 100% of their current rating at 25 degrees Celsius. Therefore, these breakers carry a continuous ampere rating rather than a pickup value. MCCBs should only be applied at 80% of their continuous current rating to maintain adequate ventilation and temperature around the MCCB. For fuses, continuous ampere ratings are also used instead of pickup ratings. Low voltage power fuses are designed to withstand 110% of their continuous rating indefinitely under controlled laboratory conditions. Both single and dual element fuses are available up to 600 volts, with the dual element fuse utilizing one element for overload and the second element for short circuit protection. Medium and high voltage power fuses typically do not operate for currents below 200% of their nominal ampere ratings. For the primary device pickup coordination to be effective, the design ratio of the backup to the primary device minimum pickup rating should be as small as possible. We also have to take in consideration the current transformer saturation. A CT transforms line current into values suitable for standard protective relays and isolates the relays from line voltages. Saturation can occur in the CTs used for electromechanical induction disk relays, low voltage ground fault current, and solid state low voltage trip devices.
So moving forward to overcurrent protection guidelines, in order to proceed with overcurrent coordination, individual load or branch circuit protection should be applied according to the required codes and standards, which is well known as the National Electrical Code or NEC, the NFPA 70-1999, American National Standards Institute or ANSI, and other codes and standards shown. Overcurrent protection devices are mostly used to protect conductors. The NEC stipulates regulations for conduction protection. These regulations often rely on the protective device's long-term pickup rating and the regular full load rating or ampacity of the conductor. Here shown in the PPT are the NEC regulations. For the motor, definite time setting for a breaker-fed motor must be set to not trip during motor starting. Electromechanical relays must be set above the asymmetrical RMS current either by the pickup or with a time delay. With modern relays, a definite time unit can be used if its setting is coordinated with the contactor interrupting rating. Transformers are vulnerable to mechanical damage as a result of the extreme forces encountered during a malfunction, in addition to insulation damage from prolonged overloads and short circuits. There are factors to consider when coordinating with transformer protective relays. Here shown in the PPT are the factors to be considered. For inrush current, the maximum inrush current usually assumed to be at 0.1 seconds and use of 8 to 12 times FLC at 0.1 second. It is an empirical approach based on EM relays. A generator's fault current contribution decays over time. Overcurrent protection must allow both for moderate overloads and be sensitive enough to detect the steady state contribution to a system fault. To avoid nuisance tripping, especially on islanded systems, higher time dials are better. For the time current curve, or also known as the TCC plots, it is the basis for carrying out any coordination study. The operating time of a protective device is determined by a TCC curve for different operating current magnitudes. So the time displayed on the coordination plot shows the amount of time that has passed since time zero, which is where the point that fault have occurred. Each device's response time for a specific fault current magnitude is represented by the relative location of the device characteristic curves on the plot. This upstream device shouldn't function until the first device has enough time or margin to identify and fix the fault in order to reduce the loss of service. There are two basic forms of characteristic curves, which the single line and banded. The single line curve characteristic of overcurrent relays indicates the approximate time that the device will close its contacts to initiate the opening of a circuit breaker. The banded curve characteristic of fuses and low voltage circuit breakers includes tolerances and operating time. Time over current relays is plotted as a single line curve. On log paper, the manufacturer provides curves for certain relays that include the time range of time delay settings that are accessible. The city ratio and top setting of the relay affect the pickup current of the relay. To sum things up, the higher the fault current magnitude, the faster the relay operates. Low voltage circuit breaker characteristics are often represented as banded curves and are available in a variety of formats. Although they can be found on ICCBs and MCCBs, electronic devices are typically used on LVPCBs. The majority of motor safety relays are static devices with a wide range of extra protection features. A few motor protection relays also have motor control capabilities. The relay can be combined with the fuse to provide short circuit protection, or it can be used for complete motor protection. It has a banded characteristic which represents the overall operating time of the fuse from the point at which it starts to melt until the fault is fully resolved. The bends, which for each fuse size correspond to the lowest melting and overall clearing time frames, are banded.
So let's now proceed to the coordination time intervals, or also known as CTIs. So first off, the CTI is the time frame between an upstream backup and the main device. When two such devices are coordinated such that the primary device should operate first at all fault levels, they are selectively coordinated. When plotting coordination curves, certain time intervals should be maintained between the curves and various protective devices to ensure selective operation and to reduce noise and slipping. Without adequate coordination time intervals, these protective devices could trip incorrectly. There are two types of molded case circuit breaker operating characteristics. The first one, the thermomagnetic, and the other one is magnet trip. Relay combinations with banded devices. The illustration on the left portrays that the relay is electromechanical, while on the right side portrays that the relay is static. The difference between the two, the disk overtravel is more applicable the electromechanical compared to the static relay. When static overcurrent relays are used, the disk overtravel component is eliminated, and the CTI can be further reduced to 0.22 seconds to 0.12 seconds. For systems using induction disk relays, this overtravel can be reduced by employing a special high dropout instantaneous element set at approximately the same pickup as the time element with its contact wired in series with the main relay contact. The CTI in this case is often reduced to 0.22 seconds to 0.12 seconds, assuming an 8-cycle breaker. So let's now proceed to the initial planning and data required for a coordination study. One of the initial planning and the data required for a coordination study is single line diagram. The research involves a new or existing system. The design has to include the following information below. We do also have here short circuit study, obtaining or performing a short circuit analysis with ratings for both momentary interrupting events. Includes inputs from each source of short circuit current as well as the greatest and lowest predicted fault interrupting task. We do also have your current scale selection. The characteristic curve of the device closest to the load is plotted as far to the left of a 4x4 cycle graph, wherein to achieve time sequence stripping of current protective equipment. The right-hand limit of the curves is where the system peak short circuit current is located. We do also have your characteristic curves. It is important to keep in mind that before attempting to evaluate coordination, all currents must be subjected to a common voltage, either primary or secondary, throughout the process of charting the time current characteristic curves. And lastly, selective coordination. The primary device of the transformer should trip on in rush, nor should the time current characteristic curves of the protective devices overlap. The protective equipment should be configured to safeguard system gear, as such as motors, cables, and gears against short circuit and overlay situations. So once again, we are EE Youth Group. We hope you learn about Chapter 15 of IEEE 242 2000-2001 BAF book, Overcurrent Coordination. That's all. Thank you for listening.